In this video, we are going to insert into a red-black tree the values 30, 10, 20, 25, 35, 26, 27, and 28. Inserting 30 and 10, 30 becomes the root and will become a black node. 10 will become the left child of 30 and will be noted as red. So here's what happens when we insert 20. 20 will initially become the right child of 10 and will be red. We notice that we have this zigzag pattern. We also notice that the uncle of 20 is black because it is a null pointer. So what's going to happen is we are going to perform what we would call an AVL tree, a double rotation where 20 is going to come up, 30 is going to become the right child of 20, and 10 will become the left child of 20. What's also going to happen is that we're going to get recoloring of 20 and 30. And now we see that we have our double rotation, and now 20 and 30 will become recolored. Since 20 is the root, it will not be changed again. Now we're going to insert 25 and 35. 25 will become the left child of 30, and here's what's going to happen. All nodes are initially inserted as red. We have a red parent, a red uncle, and a black grandparent. So what's going to happen is all three of those colors are going to change. 10 and 30 will become black, and 20 will become red. Going up to the top, we run into that case 0, where 20 will become black. We now see that there is a valid path between the root node containing the value 20 and two black nodes between every node null pointer in the tree. We're going to do the same thing with 35. 35 will become a red child and will become the right child of 30. No rotations will change in this particular tree. So now let's insert 26. Insert 26 is going to result in 26 becoming the right child of 25. We have a red parent, a red uncle, and a black grandparent. So in this particular rule, we flipped all the colors. 25 will become black, 35 will become black, and 30 will become red. Going up to the red of the top of the tree, we see that we are not going to encounter any other scenarios that require recoloring or rotations. So this is the valid red-black tree. Now we're going to insert 27. 27 is going to become the right child of 26. And we see that we have a zigzag pattern. 26 is going to move up and become the left child of 30. 25 will become the left child of 26. And we're going to see 26 and 25 change colors. And now, again, we have a valid red-black tree. We have one last element to insert for this problem. And there will be a required rotation like this on the exam. When we insert 28, it's initially going to become a red node that is the right child of 27. We have a red parent, a red uncle, and a black grandparent. So we are going to see all three of those change. 25 will now be black, 27 will now be black, and 26 will now be red. When we move up the tree, we now see that we have a violation with 26 and 30, since we know that a red node cannot be the child of another red node. Furthermore, we have a zigzag pattern, and we have a black uncle. So what are we going to do? Well, we are now going to perform the double rotation that we discussed in AVL trees. What's going to happen is 26 is going to move up, 20 is going to become its left child, and 10 will remain over here. 25 will become the right child of 20. Then 30 will become the right child of 26. And 30's left child is going to become 27. We're going to have 28 and 35 over here. When we do this rotation, what we're going to see is that we now are going to change the coloring of these nodes. So let's watch what happens. We come up here, we see that we are going to move 26 up, and now we're going to do the second rotation. 26 will move. 20 and 26 are going to recolor. And now we have our final red-black tree. We go back to our choices and we see that choice D is the correct answer.